Okay, so hi everybody, let us start. Welcome back. So before I forget, because I'm gonna get excited and forget, next Monday is a holiday, if I remember correctly. So that means no pre-recorded lecture. So that means this week's pre-recorded lecture was the last one, which is kind of sad. And yeah, let me just remind you what we did last time. So please feel free to turn on your videos. And first of all, we were trying to talk about the multivariate generalization of the Cayley formula for the number of trees. And the idea was to count trees according to their degree sequence. So you have d sub v of t denotes the degree, which is the number of neighbors of vertex v in t, and then you can just write down for each n. You can write down the polynomial fn of x1 up to xn, which is just the sum over all trees. All right, so this fat t denotes the set of trees with vertex set bracket n. And then you just take x1 to the degree of 1 in t times x2 to the degree of 2 in t, and etc. all the way up to xn to the degree of n in t. And I think I computed some examples. I don't quite remember, but so the first three examples which you can compute by hand is that for n equals to 1 you get f1 of x1 is just 1, which corresponds to the tree, the unique tree with one vertex. And for n equals to 2 you get f2 of x1 x2 was equal to x1 x2, which corresponds to the unique degree with unique tree on 1 2 with 2 vertices. And then the next one I also computed, which was already kind of tricky but manageable, x1 x2 x3, and the answer was x1 plus x2 plus x3. Well, no, this one is actually, yeah, this one was also easy. You have 3 possible trees, 1 2 3 1 2 3 1 2 3, and yeah, their degrees contribute these monomials. And finally, I think I also computed the case where n is equal to 4. And in this case, the answer was 4 of x1, x2, x3, x4 was something like this sum squared times x1, x2, x3, x4. And we also know, right, if you just plug in, so Cayley's formula tells us that if you take fn and you plug in all the x's just to be equal to 1, you specialize, then you sum all trees with weight 1, so you just get the number of trees. And that's n to the n minus 2, and that's it. So somehow if you look at these formulas, you should see that, well, sorry, this is supposed to be, wait, is it just 1? Or yeah, it's just 1, which is kind of interesting. All right, never mind. Yeah, so the claim is that this is n to the n minus 2. Every node has at least 1 degree. Well, except for this case here, right? Yeah, anyways, I guess this is sort of an exception. Why can I factor x1, x2, xn out of the right-hand side sum for n equals to 3 and n equals to 4? Right, yeah, that's so here you see that there is an extra monomial which you can explain by the fact that a tree is connected, so there is no kind of isolated vertices, and in particular every degree is at least 1. So every xi appears with degree at least 1. But in these two examples you can actually just, I was just trying to be clever here and not have to write this term 3 different times, but actually you can just x1, x2, x2 squared, x3, x1 squared, x2, x3. I mean, this sum can be just computed explicitly without any, so here's the theorem, which you can probably conjecture based on this data here. The theorem is exactly fn, x1, x2, all the way up to xn is just the sum xn to the n minus 2 times the product x1, x2, all the way up to xn. Which I think it's pretty cool. So it's you don't get this. Sometimes you get like a Q analog, so you get a polynomial in one variable equal to something nice, but to have a polynomial in n variables is pretty rare. And let me also rephrase it in a slightly different form. So in other words, this lets you count the number. You can prescribe the degree sequence. So the number of trees with degree sequence d1, d2, so just arbitrary n numbers equals, and so you get the, you ignore this part here, and well, this part decreases every degree by 1. So what you get is n minus 2, multi-choose d1 minus 1, d2 minus 2, well, so d2 minus, wait, what? d2 minus 1, all the way up to dn minus 1. Yeah, sorry, this is supposed to d2 minus 1. So, and let me remind you that well, these multinomial coefficients are non-zero if and only if what? If and only if the sum of these numbers should be equal to this number here, which is kind of surprising because these are degrees, right? Well, anyways, the this is related to the handshake lemma, right? So remember, we call this lemma that if you just take the sum of these di's, I from 1 up to n, this is equal to what? To n minus 2, right? Because that's the, and that is equal, by the lemma, it's equal to twice the number of edges of any tree, and every tree has exactly n minus 1 edges by the Euler's formula. So yeah, you have 2n minus 2. In particular, if you subtract 1 from each of them, you get exactly n minus 2 as the sum. So it checks out. Yeah. So I'm gonna prove it. Let's prove the theorem, and the proof we previously had is not gonna work here. I'm gonna slowly go through all, at least 3 different proofs of the Cayley formula. So this is the second one, which has the advantage of generalizing the result to this multivariate version. And the proof is going to be, I'm going to use Prüfer sequences. So yeah, Prüfer's code. Okay, thank you. Yes, that is the idea. And apologies to those of you who already know it from, I guess, your computer science background. But anyways, so let me give a definition. A Prüfer sequence is a very simple object, is just a sequence A of A1, A2, all the way up to n minus 2 of elements of n, bracket n. And in particular, just any sequence of n minus 2 numbers is a Prüfer sequence. And if you look at the Cayley's formula, right, the thing on the right hand side, well, the thing on the right hand side is the cardinality is the number of all Prüfer sequences. So number of all Prüfer sequences of fixed length is just n to the n minus 2. So we're going to try to come up with a bijection between such sequences and trees. And the easiest way to do this is, so the goal, all right, the goal is, and we want the multivariate analog. So the goal is to find a bijection which sends, you take a tree and then somehow you associate a sequence a of t, a n minus 2, so that I want the additional requirement. I want the degrees to, I want the vertex degrees to go to let me just write it down, so that the so that for each I in bracket n, I appears in the Prüfer sequence exactly di of t minus 1 times. So in particular, this explains the appearance of the. So basically, if you just take the sum over all Prüfer sequences of the whatever xi to the number of times I appears in the sequence, it's gonna be easily seen to factor into a sum like this times a product like this. Is that clear or is it confusing? So let me write it down. The sum over all a Prüfer sequence. So I want x1 to the number of ones in a minus 1 times x2 to the number of 2's in a minus 1 times etc. All the way up to xn. And the claim is that because I can choose the first entry in any way I want, and I can choose the second entry in any way I want, and etc. That means that for the first entry I get x1 times x1 plus x2 plus etc. plus xn. That's the options for the first entry, and the same for the second one. And anyway, so I get, I think I get just exactly this sum here. Hey, let me know if there's any questions. So the question is, how do I find such a nice bijection? And because I have this kind of strong requirement on the number of times I appears, this is sort of a hint. And in general, if you want to come up with a bijection, the stronger the requirements, the easier it should be to come up with a bijection. And the way I'm going to do that is the easiest way is to go from a tree to the code, right? That's the from a tree to the Prüfer sequence associated to the tree. And the way we're going to do that is, let me try to draw a random tree. Maybe that's too big. Something like this. 1, 2, 3, 4, 5, 6, 7, 8. So what I'm gonna do is I'm gonna find the smallest labeled leaf. So remember, a leaf is a vertex of degree 1. So the first step is to find the minimal leaf I in bracket n. So just the minimal label of a leaf, which in this case is 1, right? 1 is a leaf and 1 is the smallest number. So yeah, so let me copy this tree, and then I'm gonna modify it. So okay, so 1 is the smallest leaf, and then what I'm gonna do is I'm gonna look at the neighbor of the leaf. In this case, so let j in bracket n be the neighbor of I. There's a unique neighbor, right? Because I has degree 1. And then what I'm gonna do is I'm just gonna record j into my sequence. So even though I'm looking at the leaf 1, I'm gonna record 4. So append j to a of t and remove I from t. And then you just iterate these 3 steps. So yeah, iterate until t has 2 vertices, and then you stop. So you record exactly n minus 2 numbers. So let me try to do this in this case. So a of t is what? First, the minimal leaf is 1, so I record 4. So a of t starts with 4, and then I remove 1 from t. Okay, now I have a new tree. And now I look at the minimal leaf, which in this case is 3. So 3 is connected to 4. So now I remove 3 from my tree. Now I have now the smallest leaf is 4, which is connected to 2. So I record 2, and I remove 4 from my tree. And I just keep going. So the next one is 5. I record 2, remove 5. And the next one is 7. So I record 2, remove 7. And the next leaf is 2. So I record 6, and I remove 2. And that is a of t. So I am left with 2 vertices, at which point I'm gonna stop. So let me bring the tree back to its original place. And the observation that you're supposed to see from this algorithm easily is that the number of times each vertex appears in the code plus 1 should be equal to the degree of the corresponding vertex in the tree. So like 2 appears 3 times, and 2 has degree 4 in the tree. 4 appears twice, and 4 has degree 3. 6 appears once, it has degree 2, and all the other things don't appear in the sequence, and they have degree 1. So so we indeed satisfy the desired requirement. So for each I, in bracket n, I appears in a of t exactly di of t minus 1 times, as desired. And yeah, so this algorithm is very sort of easy, and the hard part is to show that it works, right? So that it gives us a bijection. So how do I prove that it's bijective? Yeah, so by the way, it's also clear that this sequence has the correct length, right, n minus 2, and each entry is belongs to bracket n. So yeah, the fact that the sequence is a Prüfer sequence is clear. So conversely, given a sequence A, A1, A2, all the way up to A n minus 2, I need to find, to reverse the procedure, to find a tree T such that A of T is equal to A, and show that that tree is unique. So how do I do that? And well, the answer is, first of all, the key observation is this observation here, right? That if you just give, let's say you give me a sequence, maybe, yeah, can somebody give me an arbitrary sequence of numbers? Let's try an actual experiment. Just write down in the chat a bunch of numbers, positive integers. Okay, that's okay, stop. All right, let me choose one of them. 3, 5, 4. No, that's too long. Yeah, let's do 2, 4, 4, 2, 5, 1. Okay, let's say A is 2, 4, 4, 2, 5, 1. So okay, so let's try to reconstruct. This is, the length is supposed to be n minus 2. So n is equal to what? N is equal to 8. And but the next thing I can reconstruct from the sequence is the degrees of the vertices. I can just look at how many times each number appears and add 1, and that's where I'm going to get the degrees. So okay. Let me record the steps. Step 1 is I want to reconstruct the degrees. D1, D2, all the way up to Dn. Using the observation above, right? I can uniquely, so the degrees are going to be D1. Let me just denote the degrees. 1, 2, 3, 4, 5, 6, 7, 8. The degree is number of appearances in the sequence plus 1. So 2, and then 3, and then 1, 3, 2, 1, 1, 1. Right. So I put a 3 here because 4 appears 2 times, plus 1, I get 3. Okay, and so now I can actually, so let me try to find a tree. 1, 2, 3, 4, 5, 6, 7, 8. So these are the circled numbers are the vertex labels, and then I want to record the degrees. So the degrees are 2, 3, 1, 3, 2, 1, 1, 1. So the red are degrees, and the black numbers are vertex labels. Okay, then step 2 is what you do is now you know which vertices are leaves. In the original tree, you know all the leaves are degree 1 vertices, so you can just see them exactly from if you know the degrees, you know which ones are the leaves. In particular, if you look at the algorithm, it starts by removing the minimal leaf. So let me write it down like this. If we know the degrees, then we know which vertices are leaves, and then we also know the minimal leaf, which in this case the minimal leaf is 3. 3 is the minimal leaf. Minimal leaf. Okay, and now I look at the sequence, because my algorithm tells me, okay, I should be So the algorithm starts by taking the minimal leaf and then removing it, but I record its neighbor in the sequence. So 3 is connected to a single vertex, and that vertex is recorded as the first entry of my sequence. So I know that in this case 3 should be connected to 2. 3 is connected to 2. And so let me write down the step 3 is so let me denote this leaf, let's say I. So the step 3 is you connect I to A1, right? A1 is the neighbor of I, and then you remove. Well, then what you do is you basically just reconstruct the rest recursively. So what does this mean? Well, it means that if in the original algorithm, I would remove the remove the 3 and then proceed to compute the rest of the code, and I can just ignore the 3. So but I want to kind of do this in an algorithmic way, so that I would be able to actually write a program or whatever. So the way I'm gonna do that is I'm gonna use my red numbers to denote not just the degrees, but the sort of the remaining. Let me call it the remaining degrees, which means that if I have already found an edge, right? So I found the 3 was connected to one vertex, and I already found that vertex. So let me just decrease 1, replace 1 by 0, and replace 3 by 2. So these red numbers are going to keep track of how many more edges to each vertex do I need to add. Is that clear what I'm doing? Okay, so let me now continue. I have these new red numbers, and I know that the new leaves are 6, 7, and 8. So the minimal leaf is 6, and I know that 6 is connected to 4. Okay, so I connect 6 to 4, and then I decrease the red numbers. So 6 now has a 0, and 4 now has a 2. And then so I have done 2 and 4. And the next number is, and the next minimal leaf is 7. So I know that 7 is connected to 4. Oops. 7 is connected to 4. I decrease the red numbers by 1. And okay, now here in this case the leaves are 4 and 8. So that's interesting. 4 is the minimal leaf, it's connected to 2. So I connect 4 to 2, and then I decrease the red numbers, 0 and 1. And now the minimal leaf is 2, so 2 is connected to 5. Okay, 2 is connected to 5, and then I decrease the red numbers, 0 and 1. And finally, 5 is connected to 1. Oh, no, sorry, the minimal leaf is 5, which is connected to 1. And then I decrease the red numbers. So what I'm left with, I have used all the numbers in the sequence, and I end up with 2 vertices which are supposed to have degree 1, and like an extra edge between them. So I just add the extra edge between 8 and 1, and then I decrease the numbers, and I end up with a tree. So you can now, as an exercise, you can take this tree and you can compute the Prüfer code and make sure that you get back the sequence, the random sequence that I got from the chat. So yeah, at the end, connect. Well, yeah. Anyways, you just proceed recursively, and so my way of keeping track of these numbers was a sort of an implementation of that recursion in a sense. So what is clear is that the resulting tree is the unique tree T such that A of T was equal to A. So so I have constructed a bijection which produces a tree. Cool. Okay, thank you. I agree. So yeah, and let me know if there's any questions before I no questions. Oh, there was a sequence 2, 2, 2, 33, 55, and 9. Oh, okay. Yeah, so that sequence 2, 2, 2, you can't have 30. Yeah, all the numbers in the sequence have to be at most n, right? So if n is the length plus 2, so you can't have, or maybe you meant 3, 3. Anyways, yeah. So if there is no questions, let me try to explain. So in this lecture and the next lecture, I'm gonna basically tell you a bunch of what I think are interesting facts, which some of them are going to be without proof. And yeah, let me start right now. So I'm gonna explain sort of a related fact, which is so first of all, let me try to generalize trees. So far, I'm only looking at trees on bracket n, and I want to generalize to kind of subtrees of an arbitrary subgraph. So of an arbitrary graph, sorry. So a spanning tree of a given graph G is it's a tree. Right? It has to be a tree T on the same set of vertices, but on some other set E prime, which is a subset for some E prime subset of E. So you start with a graph. You're allowed to remove some edges, but you have to preserve all the vertices, and you have to end up with a tree. So in particular, the number of spanning trees, well, even the set. Yeah, in particular, for example, the set T of n is the set of spanning trees of Kn, which Kn is the complete graph on n vertices. So, but now you can ask this question about other graphs. You don't have to take Kn, and actually, eventually I'm going to tell you a formula. There's a beautiful formula for an arbitrary graph, which you can compute the number of spanning trees in polynomial time, which is sort of unclear from this definition. But for now, let me try to consider the next. So we discussed there is the complete graph, but there is also the complete bipartite graph. The question is, what about other graphs? And let me give you the answer first for the complete bipartite graph. And that's going to be without proof. So the complete bipartite graph, which was denoted K, what is it, N KMN. Okay, M goes first. Doesn't matter. KMN. Let's say I do some example. Maybe. How can you remove an edge without removing the vertex for spanning tree? Yeah, that's a good question. So yeah, perhaps. Well, you remove the interior of the edge. You preserve the vertices. But I mean, this definition is a formal definition. E is a set of some pairs of vertices, and I take a subset of that set of pairs of vertices. So a graph is given by specifying a set of vertices and a set of edges. So I require the set of vertices to be the same. Does that answer the question, or? Yeah, let's try. I think you're going to see it in an example. Yeah, an example. Okay, let's try to do an example. Maybe K22. Let me draw K22. So it has 4 edges, and it is itself not a tree. It's not a tree because it has a cycle, right? And in particular, I have to remove some of the edges to make it into a tree. So, and I can actually, because it's a single cycle, I can just remove any edge and I immediately get a tree. So I can remove this edge or this edge. Whoops, no, okay. Or this edge, or this edge. Yeah. So the answer is I get 4 trees. And now you see that I have used my eraser to remove an edge without removing the vertices. And maybe I should try some other example, maybe K23. Something not too big. Okay, this time I'm going to be careful. So yeah, this has a lot of cycles. And let's see if I can draw all the possible trees. I'm not even sure how to. How to do this quickly. Okay, so it has 5 vertices, which means that I should leave 4 edges. So I should remove 2 edges. Let's see. Let's say I remove this edge here, then I can remove this edge here, or remove the first edge. Once I have removed the first edge, I get like a single cycle, so I can remove any edge of that cycle. And well, should I keep going? Yeah, let me just write down etc. because I'm gonna at some point I'm gonna get confused, etc. So I can't even compute how many trees are there. But anyways, let me give you a formula. So the theorem, which you will be later able to prove using the formula for arbitrary graphs, is that the number of spanning trees of k m comma n is equal to m to the n minus 1 times n to the m minus 1. So it is this nice symmetric expression. In particular for k to 3, I guess the answer was supposed to be, what is it? 2 to the 3 minus 1. 2 to the 3 minus 1 times 3 to the 2 minus 1, which is 4 times 3, which is 12. Yeah, it would have taken a while. Yeah. So yeah, for this one, I'm going to give a proof later. And in particular, so one thing I want to mention, this thing I'm not gonna prove, is that there's also there is also a multivariate version of this formula. So on the left you take the same sum as we did before, just xi to the degree of each vertex, and on the right you're going to get m is going to become the sum of the variables associated with the vertices on the left, and is going to become the sum of xi's corresponding to the vertices on the right. And so this way you can also count trees according to their degrees, which I think is beautiful. All right, any questions so far? Okay, so and I guess today I would like to, okay, it doesn't work if n or m is 1, right? I think it should work. Okay, let's try an example. Let's say m is 1. So I'm looking at k1 comma n, which looks like this. K1n is already a tree. But the formula gives m to the n minus 1. Okay, so it gives 1 to the n minus 1 times n to the 1 minus 1, which is 1. Okay. Yeah, that's a good question. All right. So any other questions? Okay. So yeah, let me discuss rooted forests, which what I'm about to say is going to sound stupid, but later, so I'm going to need rooted forests later. But for now, all I'm saying is I'm gonna give you a statement which is easy to see. First, let me give you a definition. Definition is very sort of motivated by real life, which is a forest it's a union of trees. So it's just a graph. It's a graph without cycles. AKA a union, well, a disconnected union of trees. Disconnected union of trees. So, and I'm going to be interested in rooted forests. A rooted forest is a forest plus a choice of a vertex. Let me call it a root vertex in each connected component. For example, let me draw a random forest, a random rooted forest. So maybe something like this. Yeah. So here's an example of a forest. And let me also give you an example of a. So notice how I'm allowed to have like isolated vertices and stuff. Rooted forest. For a rooted forest, I need to pick a root, and I can do it in an arbitrary way. But I have to pick just exactly one root in each connected component. So it's a very simple object. So let me now ask a question. How many rooted forests on bracket set n are there. So how many such objects, if I label the vertices by 1, 2 all the way up to n, how many different forests am I gonna get? For example, let's say I do n equals to 1 and I get, so I have a single vertex which must be a root. So I have one rooted forest. If I do the next case, n equals to 2, then I have two vertices which may or may not be connected by an edge. If they are connected, then I have, so they are labeled, right? 1, 2, 1, 2, 1, 2. And if they are disconnected, then each vertex has to be a root. If they are connected, then either one can be a root. So I have, the answer is 3 forests, 3 rooted forests. And for n equals to 3, can somebody guess the answer? I'm not gonna draw all the forests, but what is the guess? $16. Okay, nice, thank you. That is correct. Answer 16, rooted forests. And etc. So let me state this as a proposition. Proposition, which is the number of rooted forests on bracket n is equal to what? It's equal, you can see that the sequence is shifted, right? So n equals to 2, the number of trees is just 1, but the number of rooted forests is 3. So it's not n to the n minus 2, it's n plus 1 to the n minus 1. That's the claim. And so how do I prove this result? Can you use the exponential formula here? Oh, okay, that is a good idea, right? Because the exponential formula actually gives you a way to count. Yeah, I think later I'm going to give you a proof using the exponential formula. Seems countable by exponential function. Yeah, right. The exponential formula relates sort of connected structures to taken unions of yeah. Okay, I'm gonna discuss this later. Okay. Yeah. Can anybody guess a bijective proof? Let me ask you this. Make the rooted forest into a tree. Okay, how do I make a rooted forest into a tree? Okay, connect the roots. Oh, yeah, okay. Make all the roots the children of a new root. Okay, so that's what. Okay, yeah, that's almost exactly what. Almost exactly the plan. So the proof is that take a rooted forest and on bracket n, right, so I'm supposed to get a tree on n plus 1 vertices, which so naturally you can add vertex n plus 1 and connect to all the roots. And then you get a tree. Get a tree on bracket n plus 1. And then you just forget the roots. You just only remember the tree. And why can you reconstruct? How can you remember the special vertex which was connected to all the roots? Well, because the tree is labeled. It's labeled, so the vertex n plus 1 is the Conversely, given a tree on bracket n+1, you can remove n+1 and you can choose, you can designate its neighbors to be the roots. There's going to be one neighbor in each connected component. So if you have a tree like this, usually the root is drawn on top. So if this is t and this is n+1, then you can make it into a forest by just you remove n+1 and all of its make all of its neighbors the roots. So you're getting exactly the same number of connected components as the number of roots. And that's the end of the proof. And so as I predicted, it's a sort of a very simple statement, but what it's going to be useful to us in the next lecture. So I wanted to just explain this today. If you have any questions, let me know. If not, I will see you all on Friday. Let me also mention that Monday is a holiday. I don't know why. I'm just afraid that I'm going to forget to mention this. Anyway, any questions, let me know. Otherwise, see you on Friday.